Hello, hello. So, hello means shut up, shut up, shut up, shut up. Yeah, there we go. Always the same. I mean, when I teach my lectures, I say hello, which means shut up, but people don't get the hint. So shut up is more effective. So, but it serves as a welcome too. So thanks for coming, guys. So I'm going to talk about graph neural networks. This is, I gave this talk last week. I like it, so I thought that it's my job to lecture the students in this university, so that I should present it here. So before I begin, right? So there's a bunch of people that have made this work possible. The names in red are the names of the students, because if you guys are students, you know that you are the ones that do the work. We, the professors, take the credit. At the very least, you get a highlight in red. Now that's a joke here. It's not true, not true. Anyways, so let me tell you what is this about, right? So the problems in which I am interested, or the problems in which we are interested, I should say, is have to do with doing machine learning on graphs, okay? And I'm giving you 2 examples of those problems here. The problem on the left is one of authorship attribution, so you can barely see that there are different words around that ring. So these are different words of the English language, and those connections here are representing how often these 2 words appear together in a text. So different authors have different signatures, and these are things that you can utilize to tell authors apart. On the right here, you have like another example. So this, these nodes in this ring, again, they're representing users that have given different ratings to movies. And these edges here, they're representing the product of how close these users are in general times how close they are for this particular movie. So you don't expect to see strong links here, right? Because if in general we have similar tastes for movies, we should have similar tastes for this movie in particular. So what you have on the right is a sort of like a low-pass filtering of that example. Actually, if you know what collaborative filtering is, that's literally collaborative filtering, which is a way of low-pass filtering a signal on a graph. Examples that are maybe more of interest to those of us that study physical systems are these 2. On the left here, we have a swarm that is trying to coordinate on their velocities, right? And this is a distributed system that we typically model with a graph. On the right, we have a wireless communication network. So these colored things are pairs of nodes that want to talk with each other. But it's not only that you have those direct links, you also have a lot of crosstalk interference, which, again, you can model with a graph. And these are problems that we would like to solve. And in principle, perhaps you could say that, if you want to run machine learning on this, what sort of machine learning you should run? And the answer to that, actually, in the year 2019 is very clear. You should use a neural network for 2 reasons. One is you want to get a job eventually. The other one, perhaps, which is more important, is that there is overwhelming empirical and theoretical justification to choose a neural network. If you are refusing to work with a neural network, you are neglecting a lot of evidence we have that you should. The challenge, however, is that I want to run a neural network on that thing, right? That's a graph. And the things on which we know how to run neural networks are on the right. I mean, we know how to run neural networks on grids. Now, that's the challenge, essentially, right, that we want to solve in this graph. That we want to tackle or we want to address in this talk. Now, the thing is this, right? So if I want to become good at running neural networks on the structure on the left, meaning if I want to become good at running neural networks on the structure on that graph, what I need to do is somewhat clear, actually, because what we know is that the neural networks that are good at solving problems on grids, they are relying on convolutions and point-wise nonlinearities. Point-wise nonlinearities, they're just that, point-wise, so they don't change whether you have a grid or a graph. But your convolutions should change. Okay, so let me go and try and explain this a little bit. So this is what we call a convolution, okay? So we can always go ahead and describe time utilizing a graph. So here we have nodes 1 through 6, and they are connected by that line graph, right? So 1 is close to 2, 2 to 3, and so on. Or if you want to describe an image, you do it with that grid, actually a much bigger grid. But anyway, so that's generically speaking what you want to do. Now, the thing that is very interesting, guys, is that a convolution, you can always write it as a polynomial on the adjacency matrix of either of these 2 graphs. Okay? For those of you that know convolutions, this may sound a little unfamiliar. For those of you that don't know, convolutions is unfamiliar as well. So let me try and explain what's going on in here. So when you look at the first element of this polynomial, that's s to the 0, that's identity, right? So you're just looking at the value of your own signal. Node 3 is looking at the value at 3. Now when you look at the second element of this polynomial, that's s times x, which is the adjacency, right? So node 3 is looking at 2 and 4. When you look at s squared, node 3 is looking at 1, 2, 3, 4, and 5, right? So as you keep increasing the length of this polynomial, or the number of terms in this polynomial, you are looking at information that is farther and farther away. But that's the fundamental property that convolution has, right? It has this nested locality, you could call it. Okay, and if you look at things in an image, the same is true. Now, I told you, right? I want to generalize convolutions to graphs. Well, actually, there's a good reason why I am writing the convolution in such a strange way, which is that if I change the graph, I don't need to change that equation, okay? I just change the graph. Now, instead of a line or a grid, you have this arbitrary graph or these other arbitrary graphs, and I am going to choose to call this polynomial a convolution on the graph. Okay, now a little bit more of care on defining what I mean by this graph. Right, so here we have different nodes of the graph. On top of this graph, we have defined a signal. Okay, so these are values x1, x2. That's the equivalent of your time signal here or your image over there. Right, so you have the graph. On top of the graph, you have a signal. You may have weights on these edges that represent proximity. Perhaps you don't have weights on those edges. Doesn't really matter. In either case, right, I'm going to define this polynomial as my convolution. Okay, good. I'm done with convolutions, right? So I've made it all the way to the 1990s. Now I want to cross into the 21st century, which means I'm going to try and do convolutional neural networks. The thing about convolutional neural networks is that they are a very minor variation of a convolution. Okay, this is not typically how they are introduced. We talk about mimicking the human brain or whatever, but actually this is what they are. Actually, this is what CNNs are, which, as I told you earlier on, these are the ones that work, right? Fully connected neural networks, we know, do not scale. Now, these convolutional neural networks, they begin with a convolution. They compose that convolution with a pointwise nonlinearity. That's layer 1, right? And then you get the output of that. You process that with another convolution. You send that through another pointwise nonlinearity and so on, right? So you have a cascade of this. At the output of that, that's the output of your convolutional neural network. And as you can tell, right, this is, as I was saying, just a minor variation of what a convolution is. I should emphasize here that the output of the CNN depends on that tensor H, right? So that's the thing that you learn. That's the thing that you train. Now, that's the convolutional neural network, right? If I want to do now a graph neural network, well, this is what I need to do, which looks almost like a mistake, right? Because I am kind of like getting this slide and repeating it for a second time. But actually, it is not a mistake, right? Because that's what the GNN is. The only thing that changed is that in that blue box, instead of having a usual convolution, I have now a convolution that depends on that adjacency matrix or that graph shift operator, as we call it, or whatever. That's just a matrix representation of the graph. So we have here a graph So we have here a graph convolution followed by a pointwise nonlinearity and so on. Now, couple of things that I should emphasize here. The first one is this is the exact same thing, okay? There really is no difference between a CNN and a GNN. It's just the convolution is different, but the structure is otherwise identical. Second thing that I should emphasize is that in practice, I am oversimplifying things a little bit. You use multiple features per layer. You use pooling, readout layers, etc. But these are not fundamental. These are just for, or maybe they are. What I mean by not fundamental is this is just to polish around the edges. But this is the cake. You still need to decorate your cake, and that's the role of these other things. I should also emphasize here, because this will be very important later on, that in the case of the regular convolution, this output is a function of the tensor and the input. In the case of the graph neural network, it's a function of the tensor, the input, but also is a function of the particular graph in which you are executing things. Okay, now, that's it. If you have never seen graph neural networks, this is what they are. Maybe you're wondering whether these things are useful for anything, so let me try and demonstrate that they are useful for at least a couple things. And in order to do that, let me walk you through a few problems that we had been considering. The first problem that I'm going to talk about is this one of authorship attribution with word adjacency network. So now you can see the words actually. And what we are choosing to represent here are the words of the English language that are called function words. Okay, so these are the words that don't carry meaning. Like if you look at here, this is a, couple, abort, about, right? So these are not words that convey meaning, but these are the words that you use to connect our other words. So this is meaningful because these words that you use to connect are the same whether you're talking about love or whether you're talking about war, right? But if you're talking about love, you would use the word love. If you talk about war, you would use the word war. But irrespectively of what you're writing about, these words, you're going to use them more or less in the similar way. So you can think of these words as a proxy for a language's grammar. Or actually, not for that, as a proxy for your use of the language's grammar. How can we capture that? Well, we see how often or in which way you use these two words together. That constructs what we call the word adjacency network. And you can try and go ahead and utilize this tool to discriminate between different authors. Okay, so this is a close-up. These are, just in case you want to look a little more at what the actual words that we use are. Anyway, so an example of this is the following. So here on the left is a word adjacency network for Shakespeare. On the right is a word adjacency network for Marlowe, who you probably don't know who is, but Christopher Marlowe was a contemporary of Shakespeare. There's a lot of people saying that Marlowe is actually Shakespeare. Actually, if you can demonstrate that, you can win a $100,000 prize from the Marlowe Society. Yeah, very interesting. That's why we started working on this problem. And unfortunately for us, our conclusion is that no, Shakespeare is not Marlowe. So that doesn't qualify us for that prize. But anyways, these two things, the first thing you notice is that they look the same, right? But this is because these are both English language speakers. But if you squint, and I've done the squinting for you, you start appreciating differences, right? Like there's this weird line here that Marlowe utilizes that Shakespeare never utilizes, okay? So if you look at these two adjacency networks, you can tell that these two people have different writing styles. And you can use that to analyze different plays that they wrote. In particular, we analyzed Henry VI, and we concluded that there are pieces of Henry VI that Marlowe wrote, there are pieces that Shakespeare wrote, so they collaborated in that play, and that's of interest to people in Shakespearean quarters. As a matter of fact, this appeared in an English show. Now, the drawback of this tool is that constructing these adjacency networks, these word adjacency networks, takes a lot of data. You cannot construct these words if your texts are short. So if your texts are short, however, what you could do is you could go ahead and compare histograms. Now, how would you compare histograms? Well, you would compare them with a neural network, right? I told you this is what you should be doing. But what neural network? Because, these words don't have a notion of proximity. Oh, but wait, they do, right? Because that's precisely what the word adjacency network is a notion of proximity between words. So armed with that notion of proximity, we can define a graph neural network, and we utilize that graph neural network to classify individual pages. What do we do in these pages is we extract a histogram. This histogram becomes a signal that we define on top of that graph, okay? And that works actually somewhat unbelievably well. So here we are trying to pick up individual pages, which are about 1,000 words. And we're trying to pick up either Emily Bronte or Jane Austen from a pool of 22 other people that wrote at about the same time. And you can classify them with remarkable accuracy. These are different architectures, so let's not dwell on that. But anyways, that's an example of the sort of things that you can do with these graph neural networks. Is what I like to call entertaining, because this was plenty of fun, but perhaps not that useful. Let me now go into something that is not only entertaining, but useful. This is the same example that I was trying to describe at the beginning. So here we have a swarm. This is a classical problem in distributed systems. This is called the consensus problem. You're trying for these things to all move at the same velocity without crashing with each other. Now, there's obviously a notion of a network here, right, which is the proximity network between these drones. But something that is perhaps more interesting to point out is the following. Suppose that I allow you to solve this problem with central information. So there's a centralized individual. He has access to all of the position of these drones, all the velocities, and so on. If you want to coordinate the swarm with that information, the solution is trivial. You just take the average of these velocities, you call it a day, and you go do something else. However, if you want to solve this problem without access to that central coordinator, the problem becomes exceedingly difficult to solve. Okay, I personally don't know what that optimal controller should be. And actually, it's not just my fault. I think that nobody really knows what that optimal controller should be. If you want another example of this, so here you have, again, right, this is a team of agents, and the problem you're trying to solve here is a little different. You want them to achieve and maintain a formation. These guys are trying to form a triangle. And, there's wind disturbances, sensing disturbances, and so on. But regardless of those, you want to maintain that formation. Again, this is a problem that would be elementary to solve if I had access to centralized coordination. But if I do not have access to central coordination, it becomes difficult to solve. Now, as a matter of fact, this is no mystery, okay? We know very well why this happens, and this happens because of what we call the partial information structure challenge. Because what happens is the following. So at time n, node I has access to its own local information. You can know the information of your neighbors, but that information, you're going to get it with a 1 time step delay. You can know the information of your 2 hop neighbors, but that will come with delay 2, and your 3 hop neighbors, they will come with delay 3, okay? This actually creates a game because even though we are all trying to do the same, we have access to different information, so the actions that we think are optimal are different. So even though we are trying to cooperate, we end up competing. And that game is very difficult to solve. And in summary, what happens is that you would like to solve your control with this information structure. Now, this problem is so difficult to solve that you can go all the way back to 1968 and look at the work of Witzenhausen. And to a bunch of you, the word Witzenhausen counterexample is not alien. It's a very well-known paper, I should say. And what Witzenhausen counterexample says is that even if you look at a very simple linear quadratic regulator problem in a distributed setting, that optimal controller is difficult to find. Now, we've been at this for 51 years, which means I'm willing to declare that this is a problem that is beyond our ability to solve. If it is beyond our ability to solve it, well, we can resort to heuristics, right? And if we're going to resort to heuristics, why not make it data-driven heuristics? What do I mean by that? More precisely is, well, I just told you, right? That the centralized policy can be easy to compute, right? So let's go back to the example, right? So here we have these things trying to achieve a formation. If I know everything that is going on in the system, I can solve this problem. The challenge comes because I am trying to solve the problem with this partial information structure. But what I can propose is the following. Well, try to train a distributed policy that will imitate that central policy, okay? Now, and that's where the challenge arises, right? Because the choice of parametrization here, oh, by the way, what is this problem doing, right? So this P star is the centralized policy. That's the policy you're trying to learn. You're trying to train that learning parametrization, but what should this parametrization be? Well, that's where the graph filter or the graph neural network comes into consideration. Because if you go back and look at the definition I gave of those graph filters, or I call them graph convolutions, you can immediately recognize that they are respecting the information structure that is giving rise to my challenge. Why? Well, because I am here constructing the sequence of this is called the diffusion sequence or the aggregation sequence, depending on how you look at it. But in this either diffusion or aggregation sequence, this is the sequence that is used to construct graph filters, right? So here I have, s to the power of 0, s to the power of 1, s to the power of 2, s to the power of 3. And these matrix powers are inherently local computations. You can nest them, and you can always compute subsequent powers of this matrix through local computations. Okay, now, if you have now a parametrization that respects the local structure, that's it, right? So, the graph neural networks, they operate on the diffusion sequence. That diffusion sequence respects the partial information structure that's it. You could now go and substitute this H for a GNN and go and try and train that GNN to solve your distributed control problem. And if you were to do that, it works. I mean, I will show you that it works in a couple. Where I am. I will try to show you that it works in a couple minutes. But before I show you that this actually works, let me try and explain a couple of important points. Now, from the perspective of an individual node, that aggregation sequence, guys, looks the same whether you are up here and up here. What do I mean that it looks the same? Well, if two agents are observing the same input, and their k-hop neighbors are also observing the same inputs, and the local neighborhood structures of the graph are the same, then the output that the GNN produces at these two different nodes will be the same. And this is as it should be. At least is as it should be for as long as you're considering a homogeneous team. Okay, if you're looking at a heterogeneous team, this would not be true. But at the very least, there are a large number of problems, and this is true in the two that I have considered, in which this is a quite important property that you would like to leverage. Now, what we call this property is permutation covariance, okay, which means that if you permute the graph, you permute the output as well. And I will talk quite a lot about this. But at this time, I want to emphasize that this is not a choice. This is something that I really need to have for me to be able to perform offline training. What do I mean by that? Well, I told you that I'm trying to imitate the central policy. Obviously, by definition, I don't have access to this when I am running my system. But I do have access to the central policy during training. The challenge, of course, is that you want to train on this graph, but then the graph on which you execute will be different. Okay, so you want to go from this graph to that graph. Now, however, right, I mean, if you're dropping large numbers of nodes, I mean, these graphs are not going to be that different from each other. Okay, the GNN, you can run it independently of the graph structure, and your expectation here is that the graph structures are not going to be too different from each other, so that the GNN transfers from one to the other. And indeed, we, at the very least empirically, we can demonstrate that this happens. So what you have here are different examples, right? So in the left, here in green, you have the centralized controller. In blue, you have the GNN controller, and in green, you have a potential-based local controller. And you can see that the blue one is very closely mirroring the central policy. The one that is based on local potentials doesn't mirror it too closely. But what is important in this graph, right, is that you can see that all of these configurations are different, but even though the configurations are different, the same GNN works for all of them. And why does it work for all of them? Well, because all of these networks that I am observing, they're different, yet not too far away from being permutations of each other. So remember that, right? So this permutation covariance seems to be a very important property for us. I have now covered two examples. The first one was about authorship attribution. The second one is about the learning of the centralized controllers. I have yet a third one, which is about the learning of resource allocations in wireless communication networks. This is a problem that is very close, dear to my heart, because this is what I did when I was a PhD student. So we have here a bunch of nodes, and we have two canonical configurations. The one on that one, we call it an ad hoc network. This other one is a cellular network. Those colored dots, these are pairs that are trying to communicate with each other, or like a bunch of terminals that are trying to communicate with an access point. But as I told you before, right, I mean, there's a lot of interference crosstalk. But this is an interference crosstalk that you can describe with a graph. And once you have a graph, you can try and go ahead and learn a GNN-based controller for this system. Okay. Well, I am now going to try and describe this third system, right? But I am 20 minutes into my talk, so maybe it's time that I try and summarize things a little bit, okay? So what I'm trying to do, guys, is I'm trying to do machine learning on graphs, right? And for those of you that didn't arrive on time, this could be solving problems of authorship attribution, recommendation systems. So there are plenty of problems, right, where I would like to do machine learning on graphs. And the thing is this, right? So if I were to be solving problems on a grid, I would know exactly what to do. I mean, I would run a CNN, but I'm trying to solve problems on graphs. But the somewhat surprising solution to that is to not change anything, just rename what you are calling a convolution, right? A convolution is that polynomial. Actually, not even that, right? I mean, you can always write a convolution as that polynomial. change the S that defines your polynomial, and that's it. And then once you have a convolution, a CNN, it's just elementary, right? You just combine that with pointwise nonlinearities. And I told you this can be used to do authorship attribution, but very interestingly, it can be used to learn decentralized controllers. And in the case of decentralized controllers, there are two critical things that I want to emphasize. The first one is the fact that the GNN respects the information structure of your distributed system. That's the property that allows this to work. Without that property, you wouldn't be able to implement this distributedly, which is what you want. The second important property is that of transference, right? For as long as you have two graphs that are not far from being permutations of each other, you can transfer the GNN from one graph to the other, and that's necessary if you are going to implement a trained solution that you will necessarily have to execute in a graph that is different from the ones that you considered during training. Now we are now moving on to this third example, which is a wireless interference channel. In this wireless interference channel, I told you, right, there's a lot of crosstalk. For those of you that are not familiar with wireless communications, this is how things go around. So, each pair is characterized by a channel HI, but it's not the only channel present. I mean, when you transmit power into the wireless spectrum, that power makes it all over. So on top of the signal of interest that you want to receive, you also have a lot of signal that is coming from other agents, okay? At the end of the day, you have this quantity, which we call the SINR, which is the signal to interference plus noise ratio, which is the ratio between the power of interest and the power of all the other people in the network. Now, this is a problem that is very well known, okay? I mean, these phones, they work, right? So we know how to solve this problem, but actually we don't really know how to solve this problem. We know how to approximate it. I mean, the state-of-the-art solution to this is an algorithm called WMMMC. Okay. Now, let me point out something else also, which for those of you that do machine learning should be obvious, but for those of you that do wireless, it's not. Which is that if you look at this problem is very similar to a statistical learning problem. How is it? Well, I mean, this one here at the top, that's a statistical learning problem. You have a feature X, you compute something related to that feature, that's your U of X, and you take expected value over all possible values of X. In wireless, this is the exact same thing, right? I mean, you have here a feature, which is your channel H, a function that you want to compute depending on that feature, which is the power with which you're going to transmit P, and you take expected value over the distribution over all possible channels, okay? So these two things, I mean, they look very different. I mean, these ones we call them pigs, this one we call them pigs with lipstick, but they're mathematically the exact same problem, okay? And if wireless is a machine learning problem, we can parameterize it with a machine learning solution. Okay? If you can, let me repeat this. If you are a machine learning person, this sounds stupid. If you are a wireless person, this sounds very illuminating. So that's why this is here. Now that you have this learning parameterization, the question is, what should this learning parameterization be? Well, I mean, I am advocating for graph neural networks, so you're not going to be surprised to say that, yeah, let's go use a graph neural network. But maybe I'm wrong, okay? So I'm gonna give fully connected neural networks the benefit of the doubt and go ahead and try to train a fully connected neural network to solve this problem. If I have up to the order of 20 pairs, it's gonna take me a while, but the fully connected neural network will eventually work, okay? The graph neural network will train much faster because there's a smaller number of parameters to train, and both of them are going to more or less approximate the behavior of the WMMMC. Now, if you want to make it all the way to 50 pairs, there's no fully connected neural network here because we couldn't manage to train it. Maybe if we waited for a month and we got a better computer, we would have been able to. But in any event, right, I mean, the GNN can be trained easily, and somewhat surprisingly, perhaps, or maybe not surprisingly, it does end up outperforming WMMMC. Now, another advantage that the graph neural network has is, remember what I told you, right? I mean, that the coefficients that you learn are the parameters of that tensor. And once you know that tensor, you can execute it in any network. So in this particular experiment, what we are doing is we train for a network with 50 nodes, but then we start executing that for networks with 100 nodes, 150, all the way up to 500. And you can see that the graph neural network keeps scaling nicely. So there really is, well, actually, the performance gap with WMMMC keeps increasing, actually. So, in a sense, the GNN keeps doing better and better than the state-of-the-art solution, even though we have not retrained it, right? So this one here is the exact same network that we are running for when the system has 50 nodes. Now, at this point, maybe you should conclude that I should end this talk. Maybe I should quit while I'm ahead. But let me tell you something here. I'm an engineer. I believe all of you, or most of you, are engineers as well. So as an engineer, I am perfectly satisfied with this. I mean, we proposed a technique. We showed that it worked. But I also try to be a scientist. And as a scientist, I ask the question of why, right? That's a question that is specific to science, not so specific to engineering. But actually, maybe, not to offend anybody, I should not talk about scientists and engineers. Perhaps I should just talk about five-year-old children, right? So 5-year-old children, they're always asking why. I have made an effort in my life to behave like a 5-year-old child, so I will ask the question of why. Okay? Now, the tool that I am using is the following, right? So whether I am talking about lines, grids, arbitrary graphs, I am writing convolutions at these polynomials, okay? Now, I've used these GNNs, right, or these graph filters, and then the question that we should be asking is, okay, so why are these good at solving machine learning on graphs? I'm going to try and give an answer to that question. I'm not sure that I will succeed, but I can tell you for certain that we know exactly why these polynomials are good when we have images or signals in time. And this is not anything new. I mean, we have 100 years of experience on understanding the value of convolutions. Suppose here I give you a training set, right? So there's a loss function f you want to minimize, and I give you 2 choices of regressors, right? Maybe you want to train an arbitrary linear regressor, or maybe you want to train one that is based on convolutions. Now, which of these 2 should you choose? Well, you're going to tell me, yeah, go choose the convolution, because, I mean, I've repeated the word convolution like 1,000,000 times, so of course you're going to tell me that. But think about it more deeply, right? Because the convolution is a linear operation. So by definition, the blue is better than the green, right? Why? Well, because if you are minimizing both, the minimum of an arbitrary linear is going to be better than the minimum of a particular case linear. But that is on the training set, right? I mean, in reality, the convolution does better once you try it in the test set. So we say that it generalizes. And we know exactly why this happened. I mean, like, the thing is that the convolution is equivariant to time shifts, and that equivariance is multiplying the power of each sample that you say. And as a matter of fact, right, there's a fantastic, this is not me, by the way, this is a fantastic paper by Malat from 2012 that explains why this happens, and it makes a very convincing case. Now, I'm talking about convolutions, right? I mean, the CNNs inherit this property. Okay, and that's, somewhat obvious to see because you are composing convolutions with point-wise nonlinearities, right? There's nothing the point-wise nonlinearity can do to screw up your shifting variance. Now, what is the property, right, that graph convolutions have that is important? Well, I mean, the property that they have that is important is the equivariance to permutations. What do I mean by equivariance to permutations? Well, suppose here that you have this graph convolution, right? It depends on the tensor, the graph, and the input signal. You are now considering the running of the same network, okay? So do not change the tensor. The tensor is going to remain the same. But you run it on a graph that is a permute version of the blue graph, and a green signal that is a permute version of the blue signal. Well, if you permute the graph and the signal, it's rather obvious to see that you are permuting the output of the graph filter as well. And I am calling this a theorem because I fancy myself a deep thinking person, but actually the proof of that is these 4 lines, okay? So you cancel out permutation matrices and that's it. So there's nothing mysterious here. I mean, it's as I said, it's rather obvious, right? So the key, however, is that you're running the same filter tensor. You're changing the graph, you're changing the signal, you are permuting both, consistently permuting both. You're permuting them by the same matrix. Now, of course, right, the GNN compose this with point-wise nonlinearities. Nothing the point-wise nonlinearity is doing will destroy that permutation equivariance, right? So this is true for layer 1. Now you move on to layer 2. Layer 1 is equivariant. Layer 2 is equivariant as well. Layer 3 is equivariant. Doesn't matter how many layers you compose. The whole structure is permutation equivariant. And that one, I'm going to still keep fancying myself a deep person, and I'm going to still call it a theorem, although the proof of that is still elementary. Okay? In summary, guys, what is happening here that is interesting is that signal processing with graph neural networks is independent of labeling. Okay? Now, that sounds a little underwhelming, perhaps, but let me point out, okay, that the equivariant to permutations is an asset that is more valuable than you think it is. Now, for example, here I am considering a graph which I have purposefully made regular. And what happens here is the following. I mean, I am looking at this signal, and maybe this is the only signal that I see. You know, it's a signal with, you know, with these green signs, whatever. So that's the signal. I've been given like a bunch of these signals, perhaps, and I am training on them. Now, if you look at the signals that appear in the other pieces of the figure, these signals are permutations of the first one. So when you train with a graph neural network, you are learning to classify the signal without never seeing it, right? For as long as you see the signal, you're going to learn to classify this other one. And that is playing kind of like a very important role in all of these distributed systems, right? I mean, you have a myriad configurations, but you know, you see some of them, and from seeing some configurations, you learn to generalize to all of the other ones. And that largely is because of the permutation equivalence. Okay, now let me pause here for a second because I have bad news to give you. But so far, maybe I should, you know, go back and talk about good news. Okay, so we're trying to answer the question why. That's because, you know, we want to be little children. But in answering that question why, we went back to ask that question why for convolutional neural networks. Okay, and that brought us back into the issue of translation equivariance, a property that CNNs will inherit. We discussed that the generalization of that to graphs is permutation equivariance. And we saw that, yes, since you are combining filters with transformations that are pointwise, you are not screwing up your equivariance. So your equivariance keeps holding if you move into a GNN, into a graph neural network. And I pointed out, right, that this equivariance is maybe more important than you think because it allows you to generalize to examples that you have not seen. But at this point, right, the question that I should be asking is the following. I am arguing for permutation equivariance as the key that allows you to understand why the GNN works well. Well, but that is not a property of the GNN. That's a property of the graph filter that the GNN inherits. There's nothing special about the GNN that allows it to have permutation equivariance. It's the graph filter that has this property. The graph convolution, that polynomial, is the one that is permutation equivariant. So if I want to argue that indeed this is important, I need to answer one of these two questions, you know, hopefully both. Okay, the first one is, what is good about these pointwise nonlinearities? Or the second one is, what is wrong with just using linear transformations, okay? And I'm gonna try and give you answers to these two. I mean, the answer to the second one, which is, what is wrong with these linear graph convolutions, is that they can be unstable to perturbations. Maybe you get your graph, you change it just a little bit, but the output of your GNN changes a lot. The answer to one is that the opposite happens once you incorporate those nonlinearities. It is possible for you to retain stability to perturbations while retaining discriminability. I should have said, I forgot, that you know, the instability comes when you start to push the discriminative power. If you get your linear filters, you try to make them more discriminative, eventually you're going to make them unstable. For the graph neural network, that is not the case. Now, and I think that this is I consider personally this should be a beautiful analysis because we have to go into the spectral domain to answer that. And maybe this is not something that you were expecting. A spectral domain, guys, this means eigenvectors and eigenvalues. Okay, let's try and go there. I see some of my ESC 224 students here, so I'm gonna test you on this, guys, after the lecture. What we have here is this graph convolution operator, which we've written as this polynomial, okay? So fine, that we've already seen many times. Let me assume that this S has this eigenvector decomposition. I throw that eigenvector decomposition. And you will see that everything diagonalizes here, right? By which I mean that you can project y and project x on the eigenvector basis, and you end up with a diagonal operation. That's very remarkable, okay? Why? Well, because if I am looking at this diagonal operation here, this diagonal operation depends on the values of lambda, depends on the eigenvalues of the graph. However, you can still define this graph frequency response, which is a polynomial on a continuous variable. What do I mean by that? Well, just go ahead and plot this polynomial. It's just whatever, it's a function of lambda. There's nothing peculiar about the graph in this polynomial. This polynomial depends only on the filter coefficients. And let me go and emphasize that again, right? So you started from this. The output here, y, depends on the coefficients, and it depends on the graph. But when you define the frequency response, the graph disappears. The frequency response depends only on the values of the coefficients. What is the role of the graph? The role of the graph is to pick the eigenvalues that you're going to implement. Right? The blue graph has these eigenvalues. The red graph has these other eigenvalues. When you change the graph, the frequency response stays the same, but the graph changes. Okay? Now, that's the first important concept that I wanted to cover. The second one is I want to define the sort of filters that I am going to consider here. I'm going to call these filters integral Lipschitz, and are those for which the product of lambda times the derivative is bounded by a constant. If you have trouble wrapping your head around this, that's what this picture is for. Those of you familiar with wavelets, these are indeed wavelets. What this property requires is that when lambda is large, you need to have a filter that is flat, otherwise this derivative multiplied by a large number would be growing. But when you are close to 0, this derivative can be very large because it's multiplied by 0, which means that for large lambda, your filters are flat, but for large lambda, they can be very thin. Okay? In the parlance, what we say is that for large lambda, these things are not discriminating, but for small lambda, they are discriminating. Okay? Now, the third concept that I need to introduce is the concept of perturbation, okay, and this slide is there for your reference. I just want you to focus on this one here, which is the perturbation model that we are using, which is a relative perturbation model. We are multiplying the graph by an error matrix. It's not an additive error, it's a multiplicative error. Okay, now, remember, right, so I had this definition of the frequency response of the filter. I have this definition of integral Lipschitz filters, and I have this definition of the perturbation model. The theorem, and this one is somewhat a legit theorem, it's not elementary to prove, it's not that difficult either, says that if you measure the outputs of the GNNs, these outputs are Lipschitz stable with respect to the perturbation of the graph. Okay? And there are some conditions that need to hold for this to be true. I am assuming that the nonlinearity is normalized. I am assuming some structural conditions on the noise, etc. So there's things I'm not telling you, but that's on the interest of time. Now, maybe you are saying, well, I mean, so what, right? I mean, this doesn't seem like much, and actually, indeed, right? I mean, I told you, fine, go into the frequency domain. If you go into the frequency domain, I can restrict my class of filters. If I restrict my class of filters and I look at that perturbation model, I can claim Lipschitz stability with respect to that class of models. But in order for me to explain why this theorem is valuable, I need to prove it. And I'm going to go through the proof of this theorem. And that really you did not expect it was going to happen, right? That's what you earn for showing up. Let's put it that way. Now, anyways, I'm half joking here. The thing is this. In one particular case, this theorem is elementary to demonstrate, so I'm going to show you the proof of this theorem for the particular case of an edge dilation. Get your edges and multiply them by a number. Number could be, alpha very close to 1, but just a tiny little bit bigger than 1. What is going to happen, right? Well, if you look at the spectrum of the, if you look at the S, and the S is being multiplied by alpha, obviously, right, I mean, the eigenvectors are not changing, the eigenvalues are. The eigenvalues are being multiplied by alpha. What is going on? Well, if you begin with this blue spectrum, that's the spectrum of S, when you move into S hat, which is the dilated one, your eigenvalues moved a little up. Okay? So this is what's going on. Right? So you begin with the blue ones, you end up with the red ones. Now, what you can observe here is a very interesting phenomena, which is that those eigenvalues that are close to 0, they haven't moved. But those eigenvalues that are large, they've moved a lot. And that doesn't matter how small alpha is. You know, if you keep growing lambda, you will have eigenvalues that move a lot. Why is that a problem? Well, but actually, how can you prevent that problem? Well, you prevent that problem by assuming your filters are integral Lipschitz. Because if your filter is integral Lipschitz, right, well, this is the blue graph. Now the red graph has different eigenvalues. But in this picture, either the eigenvalue is not moving or the filter is not moving. Right? So either way, I'm stable through these particular deformations. Right? So I have proven that for as long as you give me Lipschitz, an integral Lipschitz filter, and my perturbations are dilations, I am stable to those, and actually Lipschitz is stable to those deformations. Now, this is valuable because if the filter is not if the filter is not Lipschitz, something like this will happen, right? Or if you allow for filters that are non-Lipschitz, this may happen. Suppose that you want to discriminate between signals, and these signals happen to have these spectral signatures, okay? So again, I'm not saying that these are useful signals, just, this is something that's going on the graph and you want to separate. And you train your filters to separate lambda n from lambda n minus 1, so good job, you've solved your machine learning task. Now, but go ahead now and assume that your graph has moved a little bit. And that will happen, right? Because this is not like time. I mean, your graph is something that you are estimating. Actually, this doesn't happen in time either. I mean, time is something that we sample with a circuit, so there's no such thing as regular time, okay? So, the graphs that we observe in reality, they're always perturbed versions of the graphs that appear in reality. That appear in our models. Now, of course, right, I mean, what's going to happen, right, is that your features will move to the red position, and the filters that you have beautifully trained to capture the red features now, they're just capturing garbage, right, because these things have moved sufficiently far away that you can't capture them anymore. Now, this is where the nonlinearity comes into the picture, okay? Why? Well, because the nonlinearities, guys, right, is like the maximum of x0, is the absolute value, is a sigmoid. All of these have one property in common, which is that all of them are demodulators. And for those of you that don't know what a demodulator is these are things that generate components in low frequency domains. So you get your signals that live in high frequencies, you send them through these pointwise nonlinearities, and you create all of that garbage, right? And if you send a different signal, you create a different sort of garbage. But the thing is that this garbage here, however garbage it is stable, meaning it is one that you can discriminate with a filter that is not sensitive to perturbations of the graph. Now that is pretty much the end of the talk, but let me summarize this part of the talk, which, if you know me, you know that this is my favorite piece. So I entice you with things at the beginning, and then I shoot you with, well, anyways, this is fun, I think. So what I'm trying to do here is to understand why this works, okay? And I think I'm providing maybe not a definitive answer, but some answer of why this works. And that answer comes in the form of stability, okay? It would be impossible for you to design linear filters that are simultaneously discriminative and stable, right? So you want to separate these features at high lambdas, or high frequencies, as I like to call them. Well, you need to design these filters that are thin. But these thin filters will end up screwing you up if you have perturbations of the graph. Now, the filters that do not screw you up are not discriminative. So you have one of two choices here. Either your filter is not discriminative at high lambdas, which means the filter is integral Lipschitz, or the filter discriminates at high frequencies, but is unstable. You can't have it both ways. But with the graph neural network, you can, right? Why? Well, because you do some rough classification of high frequencies, or rough isolation of high frequencies. You send these things through pointwise nonlinearities, you demodulate, and then you capture them in low frequency with a filter that is stable. Now, let me close with some philosophical digressions, perhaps, okay? So, we are used to hear by now that, the promise of machine learning is boundless, right? So, and I do agree with that. I agree with that, by the way, because, machine learning is just a set of tools for solving optimization problems with data, right? And, if you are solving optimization problems with data, you should ask the question, when are these problems useful? Well, when models are either unavailable or inaccurate, you rather rely on data. Or maybe your model is too complex, and in that case, you are better off using them as generators of simulated data. For the undergraduates among you, ESE 303 is about that, right? It's a stochastic systems analysis and simulation. The stochastic systems are so complex, we have models of them, but we can't analyze them, so we just simulate them. It's the same thing in reinforcement learning. We have the models, but the models are too complex. We don't use them to analyze, we use them to simulate. And the fact is that if you ask me, okay, give me an example of a system in which models are available, accurate, and simple, well, I can't, right? So you are either, the model is either not available, or it's not accurate, or it's not simple. But it's very difficult to hit that trifecta. But, even though the promise is boundless, the reality is not so much, right? And don't get me wrong here, because it may seem like I'm trash talking my colleagues, but that's not my intention, right? So the results are remarkable, they're impressive, right? When I was young, we didn't have voice recognition, right? We didn't have face recognition, anything. So the successes in the last decade have been remarkable, impressive, they look like magic. But, they are restricted, for the most part, to convolutional neural networks, okay? Now, if they rely on convolutions, right, you expect them to work only in signals that are Euclidean. And I should emphasize once more that this is because fully connected neural networks, they do not scale. You can solve problems with 5, 6, 10, 15 variables with a fully connected neural network, but it's going to be impossible to scale beyond that, and I'm using impossible purposefully, okay? It's literally impossible. The combinatorial complexity of the universe is not playing in your favor. As a matter of fact, I personally don't know of any machine learning method that works in high dimensions without exploiting signal structure. So, I messed up the title. I think that title should say the following. I don't like to believe, but yet I believe, okay? And I believe in the following 4 things. I'm a believer, in a sense, okay? One is that the promise of machine learning, indeed, is boundless, okay? So, there's many interesting problems that we would like to solve, so, we really should be focusing on this. But I do believe a couple other things, okay? Like the second one is that if we want to realize that promise, we need to succeed beyond Euclidean signals. And this is true even if you just want to become better at processing Euclidean signals, okay? So by understanding better graph signals, for example, you will learn something about your Euclidean signals. The third one, okay, is that if you want to succeed in non-Euclidean processing, you cannot just rely on your intuition. And I think I tried to give you a flavor of that in this talk. I began operating from intuition, after all. I told you this is the convolution, it's a polynomial. I'm going to call this polynomial convolution, right? So, a bunch of you should have been thinking, oh, come on, cut me a break, right? You're calling it convolution, but why do you call it convolution? Just because I chose to. But actually, I call it convolution because I had a spectral representation of it. And that spectral representation is the key to that stability analysis, okay? So it's not that I operated from my intuition. I operated from this fundamental understanding that a convolution has a spectral representation. And for as long as we have a spectral representation, instabilities at high frequencies will arise. And those point-wise nonlinearities can resolve those instabilities. And the fourth one, and that one is, I think that you cannot disagree with 1, 2, and 3. You are free to disagree with 4, of course, that's peculiar to me, right? I think that, the key here is to exploit signal structure, in particular to exploit a graph. You can also exploit groups, you can also exploit algebras, but I myself exploit graphs. So that's all I had to say, guys. So thanks a lot for coming and listening.